Good morning, all the students. Yeah, we'll now proceed with our 11th lecture under this module. Last lecture, we have seen what is instance-based learning and how is it different from other e-learners. Right? So, decision tree learning, multi-layer perceptron, or candidate elimination algorithm, finders algorithm, all these algorithms are eager learners where they learn on the entire data set. They learn on the entire set of training examples. But that doesn't happen with instance-based learning. In instance-based learning, all the training examples are initially stored and no processing will start until a new instance is given to be classified or predicted. Once the new instance is given to be classified, then it will start comparing that new instance with the existing instances based on some measures like Euclidean distance in order to compare its difference or in order to compare its similarity of the new instance with the existing instances. Now, with how many of the existing instances the new instance is similar, now to which class they belong to, majority of them to which class they belong to that class that new instance will be assigned based on majority vote, right? So if you take a plane n-dimensional space having data points like this, now a new data point is given, say plus, let us take this as a new data point. Now this instance distance from each of these existing instances is calculated. Now it is found that with some of the existing instances, it is resembling, it is almost similar, it is very near. Now among those existing instances with which it is similar, find out which is having the majority vote. In this case, either the star or circle. Say 3 stars are having similarity with the new instance and 2 circles similarity with the new instance. In that case, this new instance will be assigned to the star class rather than circle class. Okay, this is how k nearest neighbor works. If you take it as 1 nearest neighbor, then it is compared with the with at most only one neighbor. The similarity is compared with only at most one neighbor. Based on the distance, it will immediately assign to that particular class. But if it takes 3 neighbors or 4 or 5 neighbors, in that case, it will check for more number of neighbors, and based on the majority vote, it will assign the new instance to a class to which the most of the neighbors belong to based on majority vote. Okay, this is how k nearest neighbor works, or any instance based this particular distance metric will work. Now in today's class, we are going to see locally weighted regression and grid basis functions. Now, the nearest neighbor approaches described in the previous section, in the previous class, can be thought of as approximating the target function f of x at the single query point x equal to x cube. Okay, so we are taking one particular instance, one new instance, and that instance's distance with other instances is checked. So the similarity or the approximation of the target function happens only with respect to this single query point. Query point means new data instance. Remember, in this class, if I use query point, it is nothing but the new data point or the new instance that has to be classified or to be predicted. Okay. Now, if I take a new instance, approximating the target function on this new instance depends only on that particular new instance, right? It doesn't depend on the entire data set to make this function approximation for this new instance. That is what is being told here. The nearest neighbor approaches the nearest neighbor approach will approximate the target function f of x at the single query point x cube. That is the new data instance that is given. Function approximation is done only with respect to that new instance. The locally weighted regression is a generalization of this approach. So when we take locally weighted regression means when you are fitting function to a data set. In that case, you weight the attributes locally. Means you assign importances to attributes locally. That is called as locally weighted regression. You know what is a regression problem? When some data points are given in an n-dimensional plane, when you're trying to fit a line which explains the behavior of the data very well, that is called the regression line. Now, locally weighted regression is a generalization of this approach, what we are adopting in k nearest neighbor. Okay, so we are trying to add some weights to the attributes based on their importance or the range of impact they have or the range of influence they have in predicting the outcome variable. Okay, in that case we call it as locally weighted regression. Now it constructs explicit approximation to F over a local region surrounding XQ. Now we are taking a local region, say this is your data point, you take a local region surrounding this XQ in order to perform this approximation to the target function F. Okay, so it constructs an explicit approximation to F for the local region surrounding this XQ. You take a data point, now only locally it is considered. The local region or the similarities around that particular region is considered. So the approximation is done only around that local region. Now, for example, we might approximate the target function in the neighborhood surrounding XQ using a linear function or a quadratic function. It can be a linear function simply by not having any polynomial terms like x square, x cube, and so on. You just have a linear function in the form of y equal to ax plus b. Okay, that is a simple linear function. So you are trying to approximate a target function in the neighborhood of the new instance XQ. Say this is XQ using a linear function or a quadratic function having some polynomial expression like ax square plus bx plus c in that way, or a multi-layer neural network or any other functional form. Okay, let us take that as an example. Now, the phrase locally weighted regression is called local. Why? Because the function is approximated based only on data near the query point, right? Nearest neighbor means what? It is considering the data points which are neighboring to the new data instance, and that too only nearest data points, not all the data points in the data set. In that case, we call it as just local. We are we are trying to approximate the target function only local data by using only the data nearest to the new instance XQ in this case. Okay, and why we call it as weighted? Because the contribution of each training example is weighted by its distance from the query point. Now, say this data point near to this XQ, it is given larger weight. Now, some other data point is also a neighbor to this XQ, but it is little farther. It is little far away from the new data instance, so it will be given a lesser weight. Okay, so all the nearest neighbors will be given more weight and all the far neighbors will be given lesser weight. Okay, so based on this weight, we are trying to understand its contribution in predicting the class of the new instance, whether it belongs to a star class or a circle class. Okay, so that is why we are calling it as locally weighted regression. Weighted because the contribution of each training example, star training example here or circle training example here, each training example is weighted. How is it weighted? How is it given some importance, that it is playing an important role to classify XQ by assigning it a weight. How is that weight added? How is that weight assigned? By calculating its distance from the new instance. Okay, is weighted by its distance from the query point, what we have given here, XQ. And why we call it as regression? Regression because this is the term used widely in the statistical learning community for the problem of approximating real valued function. Normally, this is a thumb rule that if you're trying to predict the class of a, you're trying to predict the label of a new instance, then we call it as discrete label of a new instance, then we call it as classification task. But if you're trying to predict some numerical value, then we call it as a regression task, right? So in statistical community, we generally call regression as task of predicting the outcome variable as a continuous numerical value, right? That is why we call this method as locally weighted regression. Locally because we are taking only the neighborhood data points, weighted because we are giving them some weight based on the distance from the new instance, and regression because you are trying to predict some numerical value. Got it now? Why we call it as locally weighted regression? Now, given a new query instance XQ, the new query instance, new data point XQ, the general approach is locally weighted regression. The general approach in locally weighted regression is to construct an approximation FCAP. Why we call it an approximation? Always prediction is not deterministic value. You can't determine the value with 100% confidence. You're just guessing it, approximating it, estimating it. That is why we call it as FCAP. Instead of F, the target function is being estimated. Whenever there is estimation associated with a parameter, you have to give cap as the addition to that symbol. Okay, that defines estimated value or approximated value. Okay, now to construct an approximation of the target function FCAP that fits with the training examples in the neighborhood surrounding XQ, let us take this approach. That is locally weighted regression. Now this approximation is then used to calculate the value FCAP of XQ. What is this FCAP of XQ? The estimated classification of XQ in the case of classification task, or the predicted value of XQ in the case of regression task. Okay, so this FCAP of XQ is the estimated value of XQ, be it a regression or classification. Okay, that is the expected target value of XQ, target function associated with XQ. That is the new data instance XQ, right? Which is output as the estimated target value for the query instance, right? Now the description of FCAP may then be deleted because a different local approximation will be calculated for each distinct query instance. Say you have trained a machine learning model with locally weighted regression. Now you are giving a new data point to it in order to predict that data point's outcome. Right. Now this data point is, this new data point is this new data point's outcome is locally weighted and predicted, and once that is assigned to a particular predicted value, automatically that approximation will be deleted from the memory. Why? Because a new data point is given again, that previous approximation may not match this new data point. That is why with every new data point, whatever is the approximation made, that approximation will be deleted after that predicted value is stored. Right? That is what is given here. The description of FCAP, the estimated value of each new instance, may then be deleted because a different local approximation will be calculated for each distinct query instance. For each new data point you give, different approximations have to be made. But did you see in eager learning algorithms like decision tree? Once an approximation is done, once a function approximation is done, once a decision tree is built, that will apply for the entire set of training examples. But here it's not the case. This local function approximation is attached to each of the new data instance. Once that new data instance's predicted value is stored, immediately that local approximated function will be removed from the memory. Now let us consider the case of locally weighted regression in which the target function f is approximated near xq using a linear function of the form. You know how to develop a linear function, right? It will be in the form of ax plus bx plus c, or ax plus b, or ax plus bx plus cx plus d, like that, right? It is a linear equation without any polynomial terms like x square or x cube. Now let us consider the case of locally weighted regression, in which the target function will always be a linear equation in case of linear regression, right? So let us take the target function as f, which is approximated near x cube. Remember, it is approximated only with respect to that particular new instance x cube using a linear function of the form. How does it appear? F cap of x. F cap means estimated value of x. How is it represented? It is represented as a linear combination of weights and the attributes. Attributes and the weights assigned to those attributes. Okay, so initially we take the constant W naught, a weight when all the other attributes doesn't play any role. Extreme case, in that case it will have this bias term W naught plus W1 A1X, the weight assigned W1 to the first attribute, next W2 assigned to the second attribute, and so on, Wn weight assigned to the nth attribute. Okay, this is how you formulate a linear equation for weighted regression. Now we derive methods to choose weights that minimize squared error. Whenever you use regression, always it should strike to you that we use least squares method, right? Ordinary least squares method, in which we try to minimize the sum of squared errors. Means if there is any difference between the original value and the predicted value, find the difference, square it, sum them up, that will give you the sum squared error for that particular model, right? I'm repeating again. When you have a prediction error, find out the difference between the original value and the predicted value, square it, sum them up over all the training examples, that will give you the total prediction error, right? So that is mentioned here, that E is mentioned as 1 by 2 sigma x belongs to D for every instance of x that belongs to D. You are squaring the difference in the original value and the predicted. What is the predicted value here? The estimated value. What is the estimated value represented by? F cap of x. And what is the original value that is existing of x? What is the difference between them? It will give you prediction error. Square it, sum them up using sigma, okay, and multiply it by 1 by 2. That will give you the error. So we derive methods that minimize the squared error summed over the set of. Now, now this particular representation will lead to the gradient training rule. You remember gradient descent training rule? Whenever there is prediction error, immediately the weights will be adjusted in order to reduce that prediction error. In neural networks, you have to recollect this now. In neural networks, we have used perceptron training rule. You remember? By using gradient descent approach. What we have done there, whenever there is a prediction error, in order to reduce the prediction error, you are adjusting the weights. In this case, how do you adjust the weight in order to reduce this prediction error f of x minus f cap of x? There is some difference in the prediction, right? There is some error in the prediction. Now, how to reduce that error in the prediction? By adjusting the weights. How do you adjust the weights? You remember delta W is calculated as the learning rate multiplied by t minus O, where O is the predicted value and t is the training example that is existing, multiplied by xi, that is the input. Okay, input for which this weight have to be adjusted. This is called as the gradient descent delta value in order to adjust the weight to get minimum prediction error. Got it? You remember now? Now the same rule we are applying here also. Why? Because we are using locally weighted linear regression. So we are combining the idea of linear regression with local weights. That is why how to represent the weights here, for which you have to adjust in order to get lesser prediction error, delta Wj. How is that weight change calculated? It is nu, that is the learning rate. Read it as nu sigma x belongs to d, that is for every training instance that belongs to the set of training examples. What is the prediction error in case of t minus O? We have similar representation. F cap of x is estimated value or predicted value, and f of x is the existing value, training set example. Okay, the difference between them, f of x minus f cap of x. And what is the input here? You are trying to consider each and every attribute. So you are using aj of x. Okay, this is how the weight adjustment have to be calculated in order to reduce the prediction error, or in order to reduce the sum squared error, SSE. In order to reduce the sum squared error, we are using this weight adjustment. Okay, so say the weight is 1, that's prediction error. So you have to reduce the weight to 0.8. So that you will get a lesser prediction error, or you may have to sometimes increase the weight in order to reduce the prediction error. Say if W is 1, then you have to make it 0.8 in order to reduce the prediction error. In that case, what is delta W? 0.2 minus 0.2 to make the weight as 0.8, which will give you lesser prediction error. Got it? That is how weights have to be adjusted. Now, how shall we modify this procedure to derive a local approximation rather than a global one? Now, in this case, this is having actually a global approach. Means it is considering all the training examples prediction errors. But how to transform that into a local approximation? Because instance-based learning will use each instance at a time in order to perform comparison. This learning doesn't happen on the entire training set at a time. Okay, it is based on each instance at a time. That is why you have to convert the global approach into a local approximation approach. How to do that? The simple way is to refine the error criterion E. What is the error criterion here in this case? E equal to 1 by 2 sigma, difference between the original value and the predicted value squared. Okay. Now the simple way to redefine that error criterion E to emphasize fitting the local training examples is to consider 3 possible criteria. Okay, I'll show you what the criteria is. Now, note we write the error E of xq to emphasize the fact that now the error is being defined as a function of the query point xq. That is what I said. Remember, EQ, that is the error estimate of xq, is not measured on the entire training set. It is measured only with respect to the query point xq. That is why it is called as local linear regression. Right? Now, what are the 3-step criteria to perform this? Minimize the squared error over just the k nearest neighbors. Don't try to minimize the predicted error over all the training examples. Just try to minimize the squared error only over k nearest neighbors. Say this is the new instance. You have lots of data points. You won't consider all these data points. Instead of that, you just consider only the 3 nearest neighbors to that new instance that I marked here. Okay, so minimize the squared error over just the k nearest neighbors. In this case, 3 nearest neighbors. So how do you represent now this error estimation? E1 of x cube, that is estimated value of the new instance, data instance x cube, can be represented as 1 by 2 sigma for what all x belonging to k nearest neighbors of x cube. Means X is the set of training examples. Now this set of training examples, you are not taking entire set. You are minimizing them to just the k nearest neighbors of this new instance x cube. In this case, we are taking only 3 nearest neighbors. And you are trying to predict you are trying to calculate the error in the prediction. So what is the error in the prediction? F of x minus f cap of x. The difference between the estimated value and the existing value. Square it, sum it up for only k nearest neighbors, half it, that will give you the error approximation for x cube. That is the new data instance. Now minimize the squared error over the entire set of training examples. Let us see how it will look. Entire set of training examples, while waiting, adding weights to the error of each training example by some decreasing function k of its distance from x cube. In that case, how we can write the error estimate? We can write it as 1 by 2 sigma x belongs to d. Here we are not taking only k nearest neighbors. We are just assuming it over all the training examples. You are taking all the training examples in the data set D. And finding the prediction error square multiplied by, now what you are adding here? You are adding a function k, which is a representation of the distance between the new instance and the existing instance. Okay, so we are just minimizing the error over the entire set of D while weighting the error of each training example by some decreasing function k of its distance from x cube. So if the, in this case, what you're doing, in this case, you have considered only k nearest neighbors, okay. But in this case, you are considering all the training examples, but adding the distance measure. If the distance of the new instance with the existing instance is far, add a lesser weight. If it is nearer, add more weight. Okay, in that way you are creating a function k of d of x cube and x. That is a function of the distance between the new instance x cube and the existing instance x. Okay, that is given as the error estimate 2. Now combine both of them. The goodness of this, considering only k nearest neighbors, and the goodness of this, considering the weight of the entire set of neighbors. Combine those two. Let us see how we arrive at a final equation. Now the error estimate 3, the refined estimate E3 of this new instance x cube, how can you write now? Instead of sigma x belongs to D, you just substitute it by only k nearest neighbors. Now among those k nearest neighbors, you are giving again the weight. You understood how we arrived at the final equation? Initially, we have calculated the prediction error of only k nearest neighbors. In the next step, we have calculated the prediction error over all the training examples by associating a weight to it, weight to each of the instances based on its distance from the new instance. Now combine both of them. What do you get? You are trying to give weight to k nearest neighbors, so that among those k nearest neighbors, very near neighbors you can calculate and assign the new instance to that particular class. That is why we have added this new function k which is function of the distance between the new instance and the existing instance. Okay, so you have substituted this distance measure into this equation, and this k nearest neighbors you have brought here. So that will make your final equation 1 by 2. Sum up all the prediction error squares multiplied by their distance measures for every training example that belongs to the k nearest neighbor set. Now it is very clear, right? This is how you perform locally weighted linear regression task. This approach requires computation that grows linearly with the number of training examples. What happens here? If you increase the number of training examples, the nearest neighbors also tend to increase. Now in that case, lots of computation have to be done in order to see which number of nearest neighbors are playing an important role to predict the classification of the outcome value. To predict the value of the outcome variable. Now, criterion 3 is a good approximation actually to criterion 2. We are minimizing. In criterion 2, what we are doing in this criterion 2, we are considering all the training examples. But criterion 3 is an approximation of criterion 2. Why? Because we are using only k nearest neighbors, not all the training examples. Okay, so criterion 3 is a good approximation to criterion 2 and has the advantage that computational cost is independent of the total number of training examples. Its cost depends only on the number of k nearest neighbors considered, right? So in this case, what happens? Cost is very high because you are trying to find the distance measure with each and every training example in the data set. But in the last criterion, what you're doing, you're just taking k nearest neighbors and calculating only their distance from the new data instance. Okay, you're selecting k nearest neighbors. It may be 3 nearest neighbors or 4 nearest neighbors or 5 nearest neighbors, but you're not taking all the 100 training examples, right? That is how the training cost is reduced. Okay, its cost depends only on the number k of the neighbors considered. Now, if we choose criterion 3 and rederive the gradient descent rule, now we are slowly transforming it into gradient descent rule. We obtain the following training rule. How do you finalize this gradient descent rule now? Based on your previous understanding, derived from the 3 criteria. The weight adjustment delta Wj, the weight adjustment that have to be done to Wj is called as delta Wj. Means for this weight, if you want to adjust some weight, it is plus or minus delta Wj. So how is this weight adjustment calculated? It is the product of the learning rate nu and sigma, that is the added values of the prediction errors multiplied by the input attribute value multiplied by the function of the distance measure k, where the distance measure finds out the distance between xq, that is new instance, and x, existing instance. Okay, so did you see now delta w, which used to be new t minus o xi in the gradient descent rule, now is transformed so that it will match with this k nearest neighbor approach. So in new, the learning rate is taken as it is. Now t minus o, the prediction error also is represented by fx minus f cap of x, where f cap of x is the predicted value, which is same as o, and f of x is the predicted existing value, which is same as t in this gradient rule, right? But what additional and xi is resembling aj of x, that is the input. Now what extra thing we added so that we get a instance based learning approach? Just the function of the distance measure. K nearest neighbors you are considering, not all the training examples, only k nearest neighbors, such that their distance from the New instance xq is also considered in the calculation of weight adjustment delta wj. Got it, students? Now let us see another radial basis, another function called as radial basis function. One approach to function approximation that is closely related to distance weighted regression and also to artificial neural networks is learning with radial basis functions. So this radial basis function, same as your linear functions or polynomial functions or neural network multi-layer perceptron functions, you also have this radial basis functions, but they mainly use distance weighted regression. These also will consider distance weighted regression as its criteria in order to make the predictions. Okay, so in this approach, the learned hypothesis is a function of the form. How do you represent the function? That is the target function f cap of x. How do you represent that? W naught, the bias term or the constant term, plus sigma u equal to 1 to k, taking k nearest neighbors, WU, weight associated with each data point WU, multiplied by the distance function, that is KU. Instead of K, you're just taking it as U, where U is the instance now. We are not taking it as Q, but we are taking it as U now. Okay, both are same. KU, distance of KU, XU from X. XU is the new instance and its distance from the existing instance. That function is multiplied by the weight associated with that attribute, and all such weights are added, and that will give you the approximated value of X. Okay, here XQ is an instance from the instance set X, and where the kernel function, here we call it as kernel function. This K, before we called it as distance function or distance metric, but here we are calling it as kernel function. Whenever you're talking about radial basis functions, this any function you use to approximate the final target value, that function you call it as kernel function. Okay, so this KU d XU X, that is the distance between XU and X, the function of that KU is called as kernel function, which is defined so that it decreases as the distance of new instance from the existing instance increases. So it is like a reciprocal. This function value decreases as the distance existing instance and new instance increases. Now all the nearest neighbors for the new instance, this kernel function will increase. Why? Because the distance has reduced. You're considering only nearest neighbors. In such case, the kernel function's value will increase. Okay? So it is a reciprocal. It is inversely proportionate. If the distance decreases, the kernel function increases. If the distance increases, the kernel function decreases. Okay? K is a user-provided constant that specifies the number of kernel functions to be included. Now this K can be user-provided constant. Say if you want to find, take some 3 kernel functions, then this K will be taken as 3. If you want to consider 10 kernel functions, then that K value will be taken as 10. Okay, it can be provided by the user. Now here K is a user, yeah, that is done. If even though f cap of x is a global approximation to f of x, in this case f cap of x is a global approximation. It is not a local approximation. Why? Because we are taking all the training examples. We are not taking just the k nearest neighbors. That is why it is called as global approximation. Though f cap of x is a global approximation to f of x, the contribution from each of the ku, d, xu, x terms is localized to a region nearby to the point xu. Okay, So in this case, in this radial basis function case, though you are considering all the training examples, this kernel function will contribute so that we consider only the nearest neighbors. It will give greater weight to nearest neighbors. Why? Because the distance is increasing, kernel function's value will, sorry, the distance is decreasing, kernel function's value will increase. The distance is increasing, kernel function's value will reduce, right? So for all the nearest neighbors, this kernel function will have higher value. So that is how this global approximation will be measured in terms of localized values, nearest neighbor values. Okay, that is why this radial basis functions can be used under instance-based learning. Though the approximation is global, it is giving larger weightage to local neighbors. That is why it is called as locally approximated value of the kernels. Now it is common to choose each function, this kernel function, to be a Gaussian function centered at the point xu with some variance sigma square mu. Now, whenever you take large data sets, you always assume that it is following a Gaussian distribution or a normal distribution. For that, what is the formula? How can you represent this kernel function now? It can be represented as e to the power of 1 by 2 sigma mu square multiplied by square of the distance measure between the new instance and the existing instance. Okay, this is the formula, 1 by 2 sigma square multiplied by the distance measure. Actually, distance measure we doesn't take. This is the formula for Gaussian distribution. Now, when we are considering that this kernel function should to be a Gaussian function, then that Gaussian function's formula comes here to define the kernel. So this kernel is defined as e power 1 by 2 sigma mu square multiplied by the square of the distance measure. That is xq, distance between xq and x. Now an example radial basis function network is illustrated here in this figure. See here, you have lots of input values, input neurons, a1 of x, a2 of x based on the attributes. Now these values are passed to the hidden layer. This layer is called as hidden layer because that layer's functionality can be determined, but its input and output can't be seen. Okay, only the input is visualized on this end and the output is visualized on this end, but the input and output of this visualized. That is why it is called as hidden layer. Now what does this hidden layer do? This hidden layer takes the inputs from the attributes and it will attach some weights to those attributes based on their importance, and finally it will calculate the single output, that is the function approximated. Okay, that is f of x. Not only for single outputs but also for multiple outputs, you can design this radial basis function network, right? So this is how a radial basis function network structure looks like. Now, given a set of training examples of the RBF networks are typically trained in a two-stage process. Now, what is the two-stage process? First, the number k of hidden units is determined, and each hidden unit u is defined by using the values of xu and sigma mu square that define its kernel function ku dxu x. Okay, so what is this kernel function? It is the distance between the new instance and the existing instance. Now, how is it defined? It is defined with the help of the new instance xu and the variance in that number of neighbors, that is sigma mu square. Okay, that is used in order to define each of the units in the hidden layer. These are units, first unit, second unit, third unit in the hidden layer. Now each of those units are defined by using this xu and sigma mu square and using the kernel function k. Okay, so that will form a linear equation like W naught, that is this term, plus A1 W1 A1 X1 X, that is combination of this term, plus W2 A2 of X, that will form the next term, and so on. WK AK of X, or WK AN of X. That will give you the entire function that is approximated using this radial basis function network. Okay, so what is the second stage? First stage is to calculate each of the hidden unit U. Next, the weights WU are trained to maximize the fit of the network to the training data using the global error criterion. So each time some function is approximated like this, some value will be predicted at the output layer. Now the difference between that predicted value and the existing value, both are taken, and in order to reduce that prediction error, the weights in the hidden layer have to be adjusted in the next iteration. Now when the weights are adjusted, again it will give some prediction value, and that value's difference from the original value is tested. If the value is lesser, then the prediction error is less. But if the difference is more, then the prediction error is more. Again, one more iteration have to be taken in order to adjust the weights in the hidden layer. Okay, this is an iterative process which will finally evolve with all the adjusted weights and an ideal target function. Okay, because the kernel functions are held fixed during this second stage, the linear weight values WU can be trained very efficiently. Kernel values are not disturbed, they are kept constant. Only the weights are adjusted so that the prediction error can be reduced. This is how radial basis functions work. Now, in order to summarize radial basis function networks, provide a global approximation to the target function represented by a linear combination of many local kernel functions. So how is the target function represented? Represented as a linear combination of weights, Wi, and the kernel functions, Ku, which is the distance measured between Xu and X. Okay, so this is taken as sigma for generalized representation, where I equal to 1 to k, where k is the number of kernels you are considering. This is how you represent the ideal target function in radial basis functions. Okay, you are just taking the product of the weights and its associated kernels and adding all of them, which will give you the linear function, linear target function. Got it? Now the value for any given kernel function is non-eligible only when the input x falls into the region defined by its particular center and width. So the value for any kernel function is actually very important, but only when the input x falls into the region defined by the particular center and width. Only if it falls in this particular range, then that kernel function's value is very important. If it is falling outside a normal distribution range, then it is negligible. Okay, thus the network can be viewed as a smooth linear combination of many local approximations to the target function. So each of these kernel functions are local approximations which are actually combined in order to arrive at a global approximation. Did you understand that? Each kernel function is local approximation, and you are combining all those kernel functions in order to arrive at a final target function, which is a global approximation. Now, one key advantage to RBF networks is that they can be trained much more efficiently than feed-forward networks trained with back propagation. So it is found that it is observed that radial basis functions are more efficient at performance than when compared to back propagation in neural networks. This follows from the fact that the input layer and the output layer of an RBF is trained separately. Here, this layer is trained separately and this layer is trained separately. Both of the layers are trained separately without having any dependence between each other. That is why the efficiency of radial basis functions is its efficiency at performance, its efficiency at learning the task is far better when compared to backpropagation algorithm in neural networks. In the next session, we are going to cover on case-based reasoning. That doesn't have too much of mathematics, just the simple theory. You can easily understand that. Okay, and that will complete this instance-based learning concept. And further, we have one more concept left out, that is reinforcement learning. That will cover in next week. How did you feel about this concept, students? Is it difficult to understand? In the initial stage, it will be little confusing, but watch the video again and again. That is the advantage of online classes, because it is recorded. Whenever you have a doubt or whenever you want to recollect what all have been taught in the class, just watch the video again and again. You'll easily understand by the end. Okay, so we'll meet in the next class. Concept case-based reasoning.